Hello everyone. Today we're going to talk about series. So first we should talk about what a series is. In the past lecture, we talked about sequences, which were infinite lists of numbers. Series are kind of similar, but instead of infinite lists, they're infinite sums of numbers. Something that looks like a1 plus a2 plus a3 plus a4 and so on. Now, just like for sequences, we have a shorthand notation for series. We denote a series with the Greek capital letter sigma. Then we write the beginning and ending indices of our series. In this case, we go from n equals 1 to infinity. And then we write the formula for the nth term of our series, which in this case is a sub n. As a concrete example, consider the sum from n equals 1 to infinity of 1 over 2 to the n. This means that we start by plugging in n equals 1 to get a half, and then we plug in n equals 2 to get 1 over 2 squared, and we keep adding these terms for all natural numbers. Now, what does an infinite sum actually mean? We can't just plug in an infinite sum into our calculator. Nobody's got time for that. But we do know how to compute finite sums. In particular, if we're given a series, sum from n equals 1 to infinity of a sub n, we define the nth partial sum to be the sum of the first n terms. That is, Sn, the nth partial sum, is equal to a1 plus a2, and then we keep going until we get to an. Now, how do these partial sums help us say anything about the actual series? Well, the partial sums form a sequence that approximate the entire series to greater and greater accuracy. Since we know what it means for a sequence to converge, we can say that if the sequence of partial sum converges to some number s, then the series also converges to s. In other words, the sum of a series is equal to the limit of the partial sums. And then, if the sequence of partial sums does not converge, we say that the series diverges. So let's go back to our example of the sum from n equals 1 to infinity of 1 over 2 to the n. Does this series converge or diverge? Well, let's start by writing out the partial sums. The first partial sum is just the first term, a half. The second partial sum is 1/2 plus 1/4, which is equal to 3/4. The third partial sum is a half plus a fourth plus an eighth, which is equal to 7/8. And the fourth partial sum is a half plus a fourth plus an eighth plus a 16th, which is equal to 15 over 16. And we start to see a pattern. Let's write a formula for the nth partial sum. We see that the denominators are just powers of 2. In particular, the denominator is 2 to the n. Then the numerator is always 1 less than the denominator. So we get that the partial sum is equal to 2 to the n minus 1 over 2 to the n. Now, to decide if the series converges, we take the limit of these partial sums and find that the limit is equal to 1. Therefore, the series also converges to 1. As another example, consider the sum from n equals 1 to infinity of n. Just like before, we'll look at the partial sums. The first partial sum is just 1. The second partial sum is 1 plus 2, which is equal to 3. The third partial sum is 1 plus 2 plus 3, which is equal to 6. And the fourth partial sum is 1 plus 2 plus 3 plus 4, which is equal to 10. And now we want to try and write a formula for the general nth partial sum. It's a lot harder to do in this case, but what we find is that the nth partial sum is equal to n times n plus 1 over 2. Don't worry too much about this. We don't expect you to be able to see a formula this complicated on your own. But now that we have a formula for the nth partial sum, we can compute the series by taking the limit of the partial sums, and find that the partial sums go off to infinity. Therefore, the series diverges. For a final example, we'll talk about one of the most important series that you'll come across, the harmonic series. The harmonic series is the sum from n equals 1 to infinity of 1 over n. It's a little bit harder to see what happens with the series by analyzing its partial sums, but for now, suffice it to say that the series diverges. We'll give a nice explanation of why this is true in a future video about the integral test.